Hi, everyone, and thanks for joining us today for a NASA Google Plus Hangout on sea level rise. We've gotten a number of questions from you already online, and we'll be looking for more during today's Hangout. You can put them in the comment section on the Google Plus Hangout event page, or on Twitter using the hashtag sea level. My name is Patrick Lynch. I'm with NASA's Earth Science News team, and I'll be helping get those questions to our experts today. Today we want to talk about the basic dilemma of sea level rise, which is it has been rising over the last century or so, and that rise has been accelerating in recent decades. And the questions for scientists now are, how much is it going to rise? How fast will that rise occur? For NASA in particular, how can we measure and how can we predict that rise accurately? And for us and others, who is this going to affect ultimately? We have a great panel today to talk about just these questions. Starting in Pasadena, California at the Jet Propulsion Laboratory, Josh Willis. He's the project scientist on NASA satellite missions that study sea level, and as a scientist studies sea level rise in the role of the ocean in Earth's climate. Sophie Nowicki at Goddard Space Flight Center in Greenbelt, Maryland. Studies in particularly the physics and modeling of ice sheets and glaciers, and in the long term, the contribution that ice sheets could make to sea level rise, not just in the coming decades, but even in the coming centuries. Back in Pasadena at Jet Propulsion Laboratory, we have Michael Watkins. When he is not mission manager for the Mars Science Laboratory mission, he also works on NASA's Earth observing missions, including as project scientist for the Gravity, Recovery, and Climate Experiment, which has given scientists invaluable data in the last decade or so on changes in ice sheets in Greenland and Antarctica and other places. Down in Many, Louisiana, we have Virginia Burkett. She's the chief scientist for global change research at the U.S. Geological Survey, has been a lead author on multiple UN Intergovernmental Panel and climate change reports, and studies in particular climate change impacts on coastal communities and coastal ecosystems. And finally, in Garrison, New York, we have Andrew Revkin, Senior Fellow for Environmental Understanding at Pace University and .Earth blogger for the New York Times. So looking forward to getting your questions to everyone today. And I'll just start us off. A question for Josh. Just from a big picture perspective, can you give us kind of the current state of sea level rise research? What do we know about what's been happening in recent decades, and what do we think is going to happen in the coming decades?
Yeah, sure. Thank you, Patrick. It's a real pleasure to be here, and what a super fun way to talk about a really interesting and really important topic. I think, to me, global sea level rise is one of the most compelling pieces of sort of information we have about how the planet is changing. In a lot of ways, sea level rise is both an indicator of climate change. Remember, 2/3 of the planet is covered by oceans, and if we're looking for climate change, really we need to be looking in the oceans. But it's also an impact of climate change and global warming. Millions of people around the world live in coastal areas, and many more depend financially on those coastal areas. And billions of dollars of infrastructure is in the coastal zone. And as sea level rises over the next 100 years, we're going to have to make some tough decisions about just how to deal with that rise and how to manage it. But the big question today, I think, is just how quickly are sea levels going to rise? In the last 20 years, we've had about 6 centimeters of sea level rise. That's a few inches. It's a couple inches, about an inch per decade, a little faster than that. You know, looking out into the next 100 years, the question is, are we going to get another foot of sea level rise, or are we going to get another 5 or 6 feet of sea level rise? And as of right now, we don't have a good answer to that question. we really have big uncertainties in terms of just how much sea level we're going to be facing, sea level rise we're going to be facing. So it's an interesting time, but it's also, you know, it's a concern as well.
Right. Andy, just to keep it going here, as someone that's written about this a lot, if you have a group of people here that could answer a lot of questions, as a journalist, what's your sort of most pressing question on sea level rise to put out there?
Well, I guess one of the key things is, as Josh just pointed out, is that the unknowns that I wrote about in 1988 are the unknowns that we're still looking at right now. That's kind of, as an outside observer, you know, you think, well, doesn't science advance? But I guess, and science has advanced. Maybe you could describe how many more tools we have now than we had in 1988. But then, given that, say that it's still a hard problem. I'd like to hear a little bit more about that.
Yeah, I think you know, we're still faced with some really big challenges in terms of how the ice sheets are going to respond. You know, today we have a lot better tools just for measuring global sea level. We have satellite observations that measure sea level everywhere in the world once every 10 days very accurately. And we can actually see the march of global sea level rise as it happens. But what we still have trouble with, and what we're going to continue to have trouble with, is predicting how the great ice sheets in Greenland and Antarctica are going to respond to both the warming atmosphere and to the warming water. Recent research suggests that, in fact, the ice sheets aren't just responding to the warming atmosphere, they're responding to changes in the oceans as well. And these ocean-ice interactions are really the crux of the matter in terms of trying to predict what's going to happen in the future. There's a whole lot of uncertainty in how these things are going to respond. And you know, you bring up a good point. We've been kind of hacking away at this problem for a long time, and there have been advances, but the ice sheets are still poorly explored, poorly understood, and in some ways poorly measured. There are some things about them that we measure well, but the sort of details and the kinds of physics that are going to determine how fast sea level rises over the next century, we're still puzzling over those. And a lot of people are working really hard, but it's going to take some more time.
Another thing that's related to that is how to describe that uncertainty. And when you talk about a range that could be from essentially a yawn, you know, another 7 inches in 100 years, or 15 inches, which is a little more than what we've seen so far, to like 5 feet in 100 years, the difference is really big in terms of how societies would want to react. And when you look carefully at what scientists say, like Stefan Rahmstorf in Germany, who's been quite aggressive about, you know, worrying about global warming, at the same time he said the high end of that range is implicitly extremely unlikely. That's how he put it in A Science Perspective a couple of years ago that I wrote about on .earth. I just posted a link to it. But scientists are very reluctant to sort of rule something out. So society is stuck with this, like, you know, how quickly do we move away from shorelines? How quickly do we start buying up coastal property to get people out of ridiculously vulnerable zones? We're stuck kind of with this inability to have that conversation play out in a way that sort of our conventional norms in society can get. I don't know if you've seen any way to get progress on that. It seems like the high end seems durably uncertain.
Yeah, so Andrew, or I can take a little crack at that, and then then hand it off to Sophie maybe. Sure. You know, we spent a lot of time trying to just understand what is currently happening, right? I mean, the first step toward predicting something is understanding it, measuring it. And so we've, in the last, I would say, 10 years or 20 years, since you first started writing about this, I think we've made great strides, as Josh indicated, in measuring what's happening today, and in particular measuring the ice sheets. We've made a lot of progress. We had a mission, ICESat, that made some height measurements of the ice sheets, and we had this very cool mission called GRACE that kind of weighed the ice sheet month to month, and we're able to see how these changes were happening in West Antarctica and in Greenland. But the real problem is there's 1,000 variables that go into why the ice sheet is actually melting, right? It could be that there's warm water coming up into these fjords. It could be that there's more sun, melting from the top of the ice sheets. And so understanding the physics, taking these measurements, and then trying to map that into the physics is really the problem that scientists are wrestling with now. So I think we formed the basis to answer that question by taking all of these great measurements. But we still have a big challenge ahead in trying to sort out all the physics that's going on and what the biggest drivers in polar ice melt really is. And we continue to make these measurements. We need to make more measurements. But I would say that the big progress in the last 20 years hasn't been on prediction. It's really been on measuring. And so I think we're now poised to take that next step. But it's a really complicated step. And one of the things I like to joke about is we're in the middle of the Final Four here, and in the NCAA tournament. We know exactly what teams have won up to this point, but that doesn't really help us say who's going to win the next game, right? Because the understanding what makes a team beat another team, right? That's is the defense better, the offense, who's sick that day, who has home field advantage. All of these kind of things, get into this very complicated equation. When we talk about climate change, we're talking about millions of variables that have to get sorted out. So it really is a tough problem, and that's really the big challenge facing us today.
And just one more thing before other questions start to come in. I'm trying to share my screen. I'm not sure if you can see, but a NASA illustration that Josh is familiar with, it relates to this question of acceleration. And on my blog, anytime I post on sea level rise, this debate erupts about someone will just say in a sort of presumptive way sea level rise is accelerating, and then everyone will point to graphs like this one and say, show me the acceleration. So if you guys could discuss that a little bit, that would be great.
Yeah, I mean, the simple answer there is that time series isn't long enough to see it. So it's still small enough that over 20 years you can't really see an acceleration. Nice little graphic there. Actually, there's another graphic we could show. There's the one of the 2,000 years of sea level rise. I'm not sure if the NASA Goddard folks have that one. Or not that one, but the one in the backup material. 2,000 years of sea level rise. See if they can find it.
Yeah.
But the short answer is that the acceleration has happened really over the rates that we've seen for the last couple of thousand years. In the last 2,000 years, sea level's been fairly stable. There have been a few periods with rates of rise that are small but not insignificant. And then if you look at the last 150 years, then clearly there's been an increase in the rate of sea level rise that's quite dramatic relative to anything that's happened in the last couple thousand years. So it's in that sense that over the last 100 or 150 years, we've certainly seen an increase in the rate of sea level rise. If sea level had been rising for 3 millimeters per year for the last 2,000 years, then we would have had much higher rates of rise. Yeah.
Within that, is there any way to discriminate how much of that was a kind of rebound from the Little Ice Age versus
yeah,
something?
Let's see. I tell you what, I'll just try and share this this slide. See if this works. Yeah, here you can see that basically for the last 2,000 years, this is a sea level record from North Carolina taken in the salt marshes there that illustrates essentially what I'm talking about, that essentially we had no sea level rise for the first millennium of this record dating back about 2,000 years. And then during what's called the medieval warm period, there was a period of more rapid rise. Sea level rose about 20 centimeters in several hundred years. And then it was stable again, and the period called the Little Ice Age saw perhaps a small decline in sea level, a small downturn, but really no significant change in the rate of sea level. And then at the very end of the record, you can see the upturn, which agrees with modern day tide gauges and is about 2 millimeters per year over most of the last 100. So this is what we, it's sort of the first effort to make what you might call a hockey stick for sea level. Controversial term, but nevertheless, this is essentially what we're looking at as a record that's been fairly stable for about 2,000 years and rising really rapidly at the end.
Yeah, and Josh, actually, sea level has been relatively stable for even longer than that. The past 6,000 to 7,000 years, that's when coasts globally emerged as we know them today. And as sea level rise accelerates, we'll see another series of transgression where, like we had in the earlier part of this interglacial. So during the past 7,000 years, that's where U.S. coastlines, that's the time period in which coastlines as we know them today, all of the Mississippi Delta, for example, all of southeast Louisiana, half of that state, basically formed during that 7,000 years of relatively small changes in mean sea level.
Great. Are there any questions that have come in from the outside world yet?
We do have a number. We can get to those in a second. I want to follow up on what Virginia was saying there, and that is it has been stable, but what we know sea level has changed in the past, and I think a lot of people say when you look at these things over the very long term, well, it's changed before. What is different this time? And I think obviously the answer is there's a lot more people and infrastructure on the coast, right. But how do you answer that very basic question of, well, why does it matter what's different this time in terms of looking to the future and planning for it?
Well, one thing that's different in America, 1/2 roughly of our population lives in coastal watershed counties. And the infrastructure that's present in the coast, the societal vulnerability is, that's where it is for the United States. More than half of our GDP, some studies indicate, comes from these coastal watershed counties. So the risk, the exposure for society is much greater than it has been in past epochs of sea level change.
What's also different is the cause. In the past, the cycle of the ice ages was really driven by changes in the amount of energy we got from the sun that had to do with small shifts in the orbit and sort of angle that the Earth stood at relative to the sun. What's causing it today is human-emitted greenhouse gases and the warming that's really driven by human-caused activity.
Right. And if you look at this graphic, I believe that folks can see now, it's the relative change in mean sea level that determines whether a coast will be inundated or not. If you look at this graphic here, you'll see parts of the U.S. coast, the change in sea level looks higher. And that's because the tide gauges there and the land surface are actually sinking with respect to mean sea level. And so you can see in this graphic a much higher rate of relative sea level rise, an increase up to 6 to 8 inches in the central Gulf Coast, for example. So all places are not equally vulnerable. In some parts of the country, like off the Canadian coast there and off the Bering Straits, you can see that sea level appears to be falling, and that's because of the glacial rebound there of the land surface. And so the threat to communities and coastal ecosystems in some parts of the country are much less than along that, particularly that Atlantic and Gulf Coast shorelines.
One of the weirdest examples like that, I think, is around Juneau, from what I understand, where people are trying to figure out what to do with all this new property. Who does it belong to? That kind of thing.
Yeah, yeah. But on the North Slope, we've got not just sea level rise affecting the coastal communities there, but the temperature, another major driver associated with the changing climate here. The temperature change is causing the coastal landscape to collapse because the sediments are bound with ice. And so a lot of the coastal landscape there is more vulnerable to this temperature effect than it is to changes in mean sea level, coupled with the ice sheet retreat, which is increasing coastal erosion, and they're having to move communities off the coastline of the northern Alaska.
Virginia, I wonder if we could follow up on that. And we're going to look at a question we got from online. But if you could name sort of, let's say, 3 places in the U.S. that have a sort of a particular vulnerability to sea level rise, and then beyond here we got a question from Rana Usman on Google Plus asking what effect sea level will have on South Asian countries.
Oh, on the South Asian part, in our last IPCC report, we highlighted megadeltas as hotspots of societal vulnerability. And if you look at that report, we've got these maps showing that the Asian megadeltas are, where you've got these intense populations living on the edge, literally, in these low-lying deltaic systems that were formed when sea level rise, when their sea level was relatively stable. And the moment that sea level rise starts to accelerate, those landforms start to be transgressed by the shoreline, and the flooding is exacerbated. And then you couple that with the propensity for more intense storms. So in Asia, I'd say if you had to pick out a hotspot societally, it's the mega deltas, the large deltas in China and India and elsewhere. The Vietnam and Cambodia particularly, where you've got a low capacity for moving people out of these low-lying areas. Other hotspots in America, I've mentioned Alaska. In our coastal report that we just produced for the National Climate Assessment, 79 co-authors on that report, we have several text boxes dealing with climate change in Alaska. And so the Alaskan coastline, for reasons I've already explained, are particularly vulnerable. And if you look at this map here, you can see other places that are vulnerable. In Louisiana and Texas, for example, where the land surface is sinking up to 1 centimeter per year. And then if you put, another ½ centimeter per year or more on top of that, when you've got these environments that are no more than 1 to 2 feet above mean sea level, those environments are very likely to be inundated and lost. And again, couple that with changes in storm surge intensity, and which is also projected to increase for this particular ocean basin, where hurricanes form that make landfall in the Atlantic coast of America and along the Gulf Coast. Then those 2 drivers, in Louisiana, we lost 217 square miles of coast overnight in Hurricane Katrina. So it's not just sea level rise that is affecting these low-lying coasts, it's these other drivers as well, like the temperature in Alaska and the changes in these storm surge, the intensity or destructiveness of storms.
Right.
Patrick, we talked a little bit about uncertainty and future rates of sea level rise earlier, and I think one of the big places where that uncertainty resides is in how the ice sheets are behaving. And so maybe we could get Sophie to tell us a little bit about that and what's being understood and what the future of that sort of research entails.
Yeah, I think I wanted to answer back about your questions about uncertainty and why is it so hard to predict future sea level. The reason, to some extent, that it might seems like there hasn't been much progress compared to what you wrote many years ago, is that we do have made actually quite a lot of progress. Like, we understand a bit better how ice sheet flow and what makes a good ice sheet model. But the problem is and that's true because of all of the observations that we've made in the recent years. The tricky bit is that the more we observe ice sheets, the more we realize that there's phenomena that we don't know, that we didn't know that existed. So on the caption that's on the little movie that's being flowing, like you have a moorland that's being draining, so it's like water forming at the surface of the ice sheet that's kind of draining into the base and causing speed up. And that's a new process we had no idea existed. We still don't understand how to model it, and then what causes it. And then once we actually understand how it behaves, we would have to find a way to include it into the model. So we have made a lot of progress. We've discovered new phenomena that we know we need to incorporate in ice sheet models. But at the same time, the more we understand, the less we understand. The other reason it's very hard to make future predictions is that you really need to understand what the future is going to be. What are going to be your forcing? Is the oceans going to become warmer? Is the atmosphere going to become warmer? What are the dominant factors? So that's why projections range by a lot. You mentioned that some people believe that there is projection that in 100 years' time we would have only a few centimeters of future sea level, and there is also much more bigger numbers, such like meters of sea level rise. And that's really the problem is that you have an uncertainty in the ice sheet models, you have some uncertainty into the future projection, what's going to be the future, and then you also have some uncertainty about the current settings of the ice sheet. So, for example, what is the bed beneath the ice sheets look like? Because that's going to control how your ice sheet is going to respond. Can warm water from the ocean reach the base of the ice, whereas you know it's going to have huge effect. So for this, for example, for the bed, NASA is doing a lot of measurements of bedrocks underneath the ice sheet with Operation Icebridge. And there's very recent observations that ice sheet models didn't have until now. And if you ask me, the data is getting there and is becoming amazing, but we still need a lot to understand the current environment and the current settings in order to predict future changes.
So
one thing I might add on to that, by the way, is that I think some people might think the ice sheets are kind of just stable and then we're melting a little bit off. But otherwise they're just stable. In fact, what really happens is, it's snowing a lot and the ice sheets are growing during the winter and then they're melting off in the summer and then growing in the winter and melting off again. This is true in Antarctica and Greenland both. And so it's actually kind of the balance between those two. And as Sophie was saying, if the atmosphere changes and you get a lot more precipitation, then the amount of net ice loss is a lot less. So in fact, it's not just what's happening right on the ice sheet. It's also, how does the whole climate, how is precipitation, how is the ocean temperature? There's lots of factors that have to be solved for in understanding the future of these ice sheets. And we talked about just a couple of those variables, like what's the topography under the ice sheet. That's what Sophie was talking about. But this whole question of what is the atmosphere doing and what is the ocean doing are inseparably coupled to the future of the ice sheet. So we have to project not just the future of the ice sheet, but the future of the atmosphere and the future of the ocean, and it's a big challenge.
What are the and Sophie, you listed a bunch of them right there, but if you were to name sort of the biggest obstacle to being able to make a solid projection about the contribution of ice sheets to sea level rise, what would it be?
In my mind, the biggest obstacle is not knowing really the topography beneath the ice sheets, because it affects how much ice there is available to melt. So if you're making a cake, it kind of affects how big your cake is going to be, and also the way the bedrock is. It's going to affect how the ice is going to flow. So, for example, if you are skiing down a very nice groove ice surface, it's very easy for you to kind of slide down your slope. But then, if your bedrock is very nice and smooth, it's very easy for you to flow, and there's sediments, and so you're going to be reacting very, very strongly to any type of future changes. But then, if you are, for example, skiing over snow that's not really good quality, and you have for example, lots of patches of earth and grass sticking out, it's going to be much harder for you to slide and to behave and to move. So really, what's happening beneath the ice sheet, what the bedrock looks like, what type of geology it is going to always be one of the factors that that dominates your response. So the bed is in my mind, the biggest uncertainty. Because again, as I mentioned a bit before, the shape of the bed is going to also affect how the warm water from the ocean, the warming oceans, are going to be able to reach or not reach the ice sheets. So it's really the conditions of things that you cannot see.
I have a follow-up question related to that. So are there any remote sensing methods that can get people down there? I did write a couple of years ago about some cool work by actually a NASA scientist who dropped a camera down a Mulan to try to get a picture of the underbelly of an ice sheet. But it was very preliminary, obviously very limited in scope. So what else can be done to clarify what that interface between the ice and the rock is like?
So I'll take that one again, and then maybe afterwards George and Mike can contribute to that too. But so at the moment, NASA has this huge campaign called the Operation Ice Bridge. It's basically aircraft that are flying over Greenland and Antarctica. They have radar, and the radar gives them, the returns from the radar gives them an idea about how thick the ice sheet is. You can also try to measure from space what the geothermal heat flux beneath the ice sheet is. And NASA, again, is doing a lot of work on that. And as you said, there is also a lot of groundwork, with people dropping things in Mulans, people drilling ice cores and trying to get sensors down the ice sheets and reaching the best. So you're right, there is a lot of different type of measurements being used and giving us a clearer picture every day of what is happening down there.
Someone I remember joking about putting the rubber duckies down Mulans to see where they come out. You know, those little floating yellow ducks.
Oh, it did happen, actually.
Oh, they did that?
Yes. They did. We did have some field work with yellow ducks being put down Mulan, and also we are putting dye, colored water down the Mulan. So we can be science can be fun. We can be very creative that way. The problem is that sometimes it doesn't come out. I mean, the ducks don't always come out, and they get stuck, or they come out many years later when you're not there to observe. But the more creative you are, I guess, the better.
Cool.
It is a hard measurement to make. I mean, most of the measurements we make from space are of the surface of the Earth, right, or the surface of the ocean, and it actually is quite challenging for us to make observations of the the bedrock below the ice. We were successful a little bit in kind of weighing the ice with this GRACE mission, but a lot of what we know about the deep ocean and below the ice sheets, it has to come from basically measurements made maybe from an airplane, like an ice sounder trying to bounce radar waves off the ground and ice interface, or actually just going out in the field and drilling and doing the best you can, sort of in situ measurements. And this is true in the ocean too. A lot of what we know about the deep ocean comes from sensors that we've deployed from ships and are actually in the ocean, in the deep ocean. So it's actually the hardest things for us to measure from space. As good as we are, at NASA with making these measurements, is stuff that's below the surface. As soon as you get a meter below the surface, it's tough to see it from space.
Yeah, let me go ahead and jump in. We've got a number of questions that have been sent in from online. These are on different topics. Maybe we can just kind of go through them one off here. So Mario Rivera says the word dramatic is being used here, but will this be comparable with I guess the changes with around the Little Ice Age?
Yeah, well, excuse me, this is Josh. We talked about that just a little bit earlier, actually. They're already much bigger, the changes, than what occurred during the Little Ice Age, especially in terms of sea level rise. We have this really amazing record from North Carolina that shows well, really very little change in sea level there during what's referred to as the Little Ice Age. And then the dramatic roughly 2 millimeters per year rise that we've seen over most of the last 100 years. So we've already really outpaced anything that's happened during the Little Ice Age and are off into new territory here.
Okay. I'll throw out another one here that just says, Josh, you showed the 2,000-year sea level rise record in North Carolina. It says, how was that data collected?
That's a great question. It's actually kind of a neat story. It turns out that the coast there, as Virginia mentioned earlier, is sinking slightly. This is due to the end of the last ice age. About 20,000 years ago, there were big ice sheets over a lot of North America, and these compressed the land there. And as those melted and disappeared, then the land under the ice sheets uplifted, and the land further away started to sink. And the coastline where these were collected, it is in one of those regions that's slowly sinking over the past many thousand years. This has been going on. And it turns out that that particular coastline contains salt marshes. And in these marshes, there are small critters that live in a very narrow band of the tidal zone. In addition, particularly on that coast, the tidal range is very small. And all this allows researchers to go back and drill cores down through the sediments created in this salt marsh, and essentially make a record back in time over exactly how relative sea level has changed. Now we can compute and measure the sort of ongoing sinking rate, and extrapolating that back over time, you can essentially get the record that I showed, almost really one of the most accurate in both vertical dimension as well as in time records of sea level rise anywhere in the last anywhere in the world. So it's really kind of an amazing detective story, and researchers are doing a lot of interesting work to reconstruct how sea level has changed in the last several thousand years. And this is one of those really cool success stories there.
Well, and to follow up with that on the detective work, Tom Notes asks, what about post-glacial rebound, which we've talked about a bit, but maybe to put a finer point on that question is, how do you determine how much rise is occurring due to post-glacial rebound and how much is occurring due to either thermal expansion or ice sheets melting? I guess, how do you sort of divide the
I don't mean to sort of take over the throne here for so long answering all these questions, but in that particular case, essentially the rate of sinking has been very accurately calculated and is stable over the course of several thousand years. So this is a place without a lot of tectonic activity where you have big changes that happen all of a sudden. Really, this is a reaction to that ice that disappeared 20,000 years ago. And so they can compute fairly accurately the rate of sinking, and you can measure it in present day as well. So it's a combination of all those things that gives us this sort of model of how post-glacial rebound is affecting the local sea level, and that can be removed fairly accurately.
Okay, we're still getting a bunch here, so let me throw this out on it. I think this is sort of the question to end all questions on sea level rise, but it is. Let me just scroll away here. How much rise becomes significant enough to provoke a response, and how do we plan accordingly for the medium to long term? Virginia, why don't we throw that to you first, since you've looked mostly at mitigation and adaptation. I think you're on mute.
Coastal systems often are noted to have a threshold at which a response is very evident to us. just a gradual increase in sea level may occur and have very minor impacts on the rate of erosion or retreat of a shoreline until a storm comes along. And then we see these dramatic changes. I think we have a graphic showing Dauphin Island off of the Alabama coast. It's a real good example of how a threshold has been breached here. The Chandler Island chain, I can think of many places where the response of a coastal system may go along very slow, and then all of a sudden you may have the salinity change to a point where the forest will die off. We've seen that off the Florida coast, for example. So there are thresholds in systems, and that's why you can't just project, U.S.-wide or even globally exactly how much land will be lost at a certain rate of sea level rise, because each system has its own internal responses depending upon the rate of uplift or subsidence, their salinity tolerance of the plants that bind the soil. A lot of variables influence that coastal response. But the question that we have kind of points to this fact that there are thresholds in systems, and we have some evidence that thresholds have been crossed in some U.S. coastal systems in terms of their ability to keep pace with sea level rise. Marshes accumulate material vertically, but it comes to a point where they can't keep pace if sea level rise accelerates, and ultimately they can be drowned in place rather than either accreting vertically or migrating inland.
One thing I would add to what Virginia's saying, Virginia actually mentioned it earlier, and that is that the interaction of sea level rise with storms is also something to really keep in mind, particularly in these low-lying areas, like in New Orleans and the Gulf Coast. It's not just the sea level rise inundating; it's sea level rise coupled with storms or more frequent storms, causing the sum of those two things to inundate much more areas. And of course, the kind of things we saw with Katrina or with other storm activities, could certainly get a lot worse. And so those, it's not just straight sea level, coming up like a bathtub filling. It's that plus storm surge.
Right.
Let me thanks for throwing that in, Michael, because that actually answered a number of questions that had come in. People are asking about the link between how sea level rise will affect other weather phenomenon. We have two questions here that kind of go together, so I'll throw these out. One is from Bruce Karen, one is from, I think, a congressional committee. It says, are there new NASA data resources that are planned to help study sea level changes in the next 10 years? And similarly, what further research investments are necessary to better understand the relationship between sea level rise and extreme weather? Michael, as the engineer, maybe looking.
Sure. So we have two satellites that have measured the ice sheets a lot, by the way, and that's the ICESat and GRACE. And we actually have replacements for both of those missions in work by NASA. So we have an ICESat-2 coming that should make very detailed measurements of the elevation of the ice sheets over Greenland and Antarctica to help us understand the kind of questions that Sophie was talking about. We also have a GRACE, basically a GRACE-2, a GRACE follow-on mission that's going to continue doing this weighing of the ice sheets every month, so that again, we can try to understand that glacial contributions to sea level rise and to try to get a better understanding what physical climate process is causing that ice melt. We also continue our series of observations of the ocean surface. We have a joint series of missions that have been going for about 20 years with the French Space Agency. We call those the Jason satellites, and they measure the sea surface height very accurately. And the sea surface height is a combination of how much water is in the ocean as well as how much it's thermally expanding. And by comparing those measurements with GRACE measurements and with some in situ measurements of the temperature and salinity in the ocean, we can get a much better idea of what's driving sea level rise, from the oceanographic perspective as well. And so we continue these kind of measurements, for the next decade or so, and we think it will help. In addition to all of the airborne and in situ, field campaigns that that folks are doing to try to get a handle on this. And when I talk about sea level rise here, as Josh said in the very beginning of this, sea level rise is an indicator of what's going on on the Earth, right? It's not the cause; it's the result of things that are going on. So in fact, we also continue all of the weather observations and atmospheric observations as well to try to understand, are precipitation patterns changing? Is atmospheric temperature changing, and how do those interact with with the kind of factors, particularly in the ice sheets that are driving sea level rise.
So,
yeah, if I sorry, go ahead, Andy.
Well, actually, this question is for all of you, but Michael, particularly looking at these planned projects, how many of them are secure in terms of our budget, given what's going on with discussions in Washington?
I think the ones I mentioned are pretty secure. They're well into development. So, the JASON missions, the GRACE follow-on, and the ICESat-2 are deep into development, and I think those are, very, very high probability that those will continue. And in fact, the support for Earth science is actually quite strong now, and so there's a pretty robust observation program to help us, sort out what's really going on. And I think those missions are pretty safe. Josh, did you have a comment you were going to make there?
Well, yeah, and just to tack on to that, I think the, missions being safe is sort of a relative term. We've continued to struggle with budget issues, even on the JASON missions, where they've continued to cause delays in the launch. And I think that, as an agency, NASA and its partners are in some ways actually struggling to figure out how to make ongoing repetitive missions happen and tie together these long records of measurements from space. It's an engineering challenge, but it's more than that. I think it's really a challenge to our persistence and a challenge to our will to keep these missions flying and to make them continuous from one mission to the next. So while a lot of, as Mike says, a lot of the things on the horizon have a positive outlook. We're not ringing alarm bells. There are still challenges, both scientific engineering and budgetary. So we have to continue to be vigilant here and press that these things carry on. Making continuous measurements isn't easy, and it requires a certain will to do so. And we're still trying to figure out how to demonstrate that we actually have that will.
Just a real quick follow-up to that, Michael, you talked about budget being secure and you feel okay with that, but what about the timeline, getting to Josh's point about continuity of measurements? Does the timeline seem okay?
Well, that's a good question. I think we started this off talking in response to your original question, which is how much do you have to measure in order until you understand? And I think we've had a hard time saying one mission's enough, 5 years is enough, or 10 years is enough. It may turn out, because of the complexity of the system, that we need a long series of missions. And I think Josh's point is we have to learn how to do that as a society. How are we going to invest in long-term observations until we understand it, and how well do you have to understand it in order to answer pressing societal questions? When are coastlines in jeopardy, or other ecosystems? And actually, and like Sophie was talking about this too, we actually don't quite know the answer to this yet. So we are still learning how much observation we need to answer the most pressing questions. And in that sense, it's not easy to say just fund one more mission and that's enough. And so we're, I think as a science community and an engineering community are working together to try to get a better answer to that question, so that it's not an infinite amount of money forever, but it's not one more mission either.
I think I wanted to add to this point, Michael, that you're very right of the difficulty when you have a budget that's defined is that you have to find the right balance between how much you are willing to continue observing the way you are and the current missions that NASA did for many, many years, and how much you want to develop new missions that are going to tell you something new. And it's a very tough balance, because the long-term trends, for example, that gives you information on how the surface temperature have changed over the ice sheet since the 70s, are extremely important in order to understand what's happening and for the modeling to test the models. So you need to continue them. And then at the same meantime, as I mentioned, I think before, it's true that for me the biggest unknown is what's happening beneath the bed, and so I would love NASA to invest into missions that will tell you more about conditions underneath the ice sheets, and it's a very hard trade-off to know really. Do you need to have something new, or do you continue the long time? And as I think the right way is to do both, because for the modeling part of you need to understand the new observations, but you also need to make sure you have the very long-term trends.
Okay, let's jump back. We have a number of great questions coming in here. Tony Himmel asks, is there any evidence showing that the North Atlantic conveyor belt is being affected by the melting of the Greenland ice sheet?
That's a good question. The short answer is no. There is no evidence that the overturning circulation, which is popularly referred to as the conveyor belt, is slowing down in response to Greenland melting. It's been predicted that it will slow down over the next 100 years, but mostly not due to ice loss due to changes in just the surface temperature of the oceans and the amount of rainfall and evaporation and so forth. But this is a good point, that we expect not just sea levels to change, but also ocean sort of climate conditions to change in the coming decades and century. And these will have implications on rainfall, on regional climate, and so forth, and may eventually have some feedbacks in terms of global climate. But we really don't yet see any major change in the ocean's conveyor belt or the overturning circulation.
Okay. Here's another good one from Paul Magnus, who asks, what about risk? How do we apply the risk of a potential 2 meter rise compared to a 5 centimeter rise? He says, I don't think people are adequately taking into account risk here. Virginia, again, is that one that you want to take up?
Sure. A very good question and a very good point. You know, as has been explained very well here, we don't know exactly the rate of future sea level rise. And so what most scientists have agreed to is kind of a range of plausible changes in mean sea level through this century. And so what I would advise, and I work a lot with coastal states and communities, is considering a range of sea level rise. The question for Mr. Magnus is 2 centimeters versus 5 centimeters. Well, I would consider that range.
5 meters, I think. 2 centimeters versus 5 meters was his question.
Oh, 2 meters versus 5 centimeters. Yeah.
Yeah, right.
And the rate of, you know, if we were to pick one number, we'd probably give you the wrong number. And so in our reports and in our assessments that we do internationally and for the United States, presenting this range of change that the scientists and the modeling results generally agree to, in presenting you with that range. And how do you apply that? You know, why such a large range? Well, as Mr. Magnus points out, it depends on how much risk that the community or the industry is willing to, or needs to consider. If you're talking about locating a power plant, for example, in a coastal zone, you might want to consider that higher range is possible. It's in the literature, even though the mid-range may be 1 to 4 feet. You know, some of the literature suggests it might be higher. If you're just restoring the vegetation on a barrier island that doesn't cost a lot of money, that 2 meter range may not be important to you. So like he had pointed out, considering the risk, you know, using this range of scenarios is important. In Louisiana, for their master plan, and I said that 50% of the state was coastal delta. It's not. It's 54% of the state is geologic floodplain, but a lot of that geologic floodplain is in the coastal zone. And in their restoration plans, they consider 2 scenarios of sea level rise: a low range and a more aggressive range of sea level rise. And for every project they have for their coastal protection master plan, they analyzed cost and benefits under the low range and the high range. And then they made the decisions based upon that, both range, the entire range, not just the high or the low.
Okay, we got a number of questions here. Actually, wondering whether sea level rise will affect the Great Lakes. Is there any indication that that would be the case?
I think the short answer is no.
No. Okay. Different systems entirely.
Although, can I kind of interject one thing is related?
Sure.
A year or so ago, I think Josh was involved in work that showed that one of the big short-term, I think you called it a pothole in sea level rise trend, was because a lot of water got piled up on the continents, which is kind of relevant in a way. You know, could you just kind of get at that it isn't just thermal expansion and melting glaciers, but water on short timescales, water can actually just sort of move onto the land if there's a lot of rain and that kind of thing. Could you talk about that?
Yeah, it was really neat. It's kind of one of the fun success stories of our satellite missions. We can measure sea level rise with an accuracy of a few millimeters now over a few month period in terms of the global mean. And between 2010 and 2011, there was about a 5 millimeter or half a centimeter drop in global sea level. And so we puzzled about it for a while. We wondered, well, maybe the oceans cooled off and shrank a little bit. Whenever water gets warm, it expands. When it gets cold, it shrinks. And this is a contributor to sea level change. But it turned out that that wasn't the case. It turned out that, in fact, water had been evaporated out of the ocean, rained down over the continents, and it was stored there for a period of about 6 months or a year. And the reason we know this, thanks, Andy, there we go.
Yeah.
The reason we know this is really because of one of our other satellite missions called GRACE. And GRACE is a gravity mission. It essentially weighs the continents from space. And you can see a big loss in mass in Australia and in Brazil, and this, or excuse me, a big gain in mass in Australia and Brazil, and a few other places on the continents around the planet. And this gain essentially equaled the amount of water lost from the oceans. So GRACE actually allowed us to see the water disappear from the oceans and then reappear over the continents. And it was in large part due to a climate phenomenon called El Nino, or really the El Nino-La Nina oscillation. In 2011 we had a big, or 2010 we had a big El Nino, and in 2011 we had a big La Nina. And these patterns in the Pacific shift the jet stream around and change the regions that receive most of the precipitation. And so in this case, it worked in such a way that water was temporarily evaporated out of the ocean and stored on land. What was interesting was that because we knew where the water kind of went, we had a good sense that it would run back into the ocean fairly quickly, and that's exactly what happened. In 2012, we had extremely rapid sea level rise, and it essentially all the water that was sort of temporarily stored wound up running back into the oceans.
Okay. We're getting up against an hour here, so maybe we'll do a couple quick questions.
Sure.
This one is a little offbeat, but I thought it was an interesting question. And Michael, this may be for you. If I ask, if sea level is rising, what does that mean as far as where, let's say, the height of something like Mount Everest would be calculated from? So it's kind of a geek question. In other words, we're always saying everything is relative to what's at height above sea level. At what point does that change, and at what point does that change the definition of how tall Mount Everest is?
Yeah, that's kind of an interesting question. You know, it's just a matter kind of how we choose to say it. Right now, we do give a height above kind of an average surface, kind of an average mean sea level. That mean sea level is not a real surface. It's kind of a fictitious surface because there's waves and there's oceanography going on all the time, and so we kind of have just chosen a reference surface for for how we measure heights. And if it changes significantly enough, we could choose 50 years or 100 years from now, we could choose a different reference height. And there are international, believe it or not, there are international organizations that try to make all countries have the same reference heights and reference everything to the same kind of zero value, and those international organizations meet and they try to make sure that the heights in the U.S. and the heights in Germany are referenced to the same thing, and those groups will continue to meet, and if the sea level rise is significant, they could choose a new reference value.
Okay. I've got one more question, then maybe I'll throw it to Andy for one final question to wrap us up here. But mine is, and I don't know if this is for Sophie and Virginia maybe, and you may not know the answer, but coming up soon will be the 5th IPCC report, which kind of gives everyone a baseline to talk about in terms of a lot of climate change indicators and things that are going on. With sea level rise, the big thing last time was that it did not include contribution. The projections did not include a contribution from Antarctica and Greenland. Can we expect that the upcoming report this time will include that, or do we know?
I'll say definitely yes, it will. Because basically the fact that the projections did not include dynamic ice sheets, everyone in the glaciology community, so all of the modelers and the field scientists took that kind of badly. We kind of thought that we were not contributing or doing a job well. And so we really focused the last 5 years on trying to kind of improve our understanding. In particular, there has been a huge efforts in Europe, a project called Ice2Sea. There was a lot of scientists involved trying to tackle that question. NASA had its own little effort called SeaRISE, which I helped co-lead, and where basically we took all the existing ice sheet models that we had and tried to understand the future dynamics. So what we're finding is that it's actually quite tricky to include the dynamical response because of factors that I had mentioned at the beginning, such like you don't really know the settings or the bed effects. We're finding that it's becoming quite important. You don't really know what your future forcings are going to be, but you definitely will read in the IPCC some of the improvements that we have made over the last few years.
Okay, great. Well, Andy, why don't I throw it to you? Do you have a question to maybe to wrap us up on? Putting you on the spot on that, but.
Well, again, 20 years ago, 25 years ago, when I wrote my first long global warming article and interviewed Kerry Emanuel and Bob Budemeyer and all these people about sea level rise, the same questions had the same answer. There was a rough sense of a 3 feet rise possible by some point in the century, and we're kind of still there. So I guess in that sense, societies, I guess it doesn't sound like society should stand and wait for scientists to come out with some clearer answer, that we have to find a way to act in coastal regions, many of which are implicitly vulnerable to coastal risks, like hurricanes. New York City had a terrible one in 1823. We just have to act more wisely in these areas. But is there anything that could it be better for the science community to say, we're not going to give you a clearer answer anytime soon, you've got to get busy now? Is that a better way, do you think, to state the case, rather than, and all of the science is really important, but I just want to get the sense that society too often has this expectation, well, we'll learn more next year, therefore so we can just wait a little longer. Is that kind of not the way we should be thinking societally?
I think that's a great question, Andy. I think that we have to begin to prepare. I mean, it's true that there's uncertainty, and it's important. It's non-trivial uncertainty. There's the difference between 1 foot and 5 or 6 feet is a big deal. But we are going to get some more sea level rise. There's no uncertainty about the sign. And
for centuries, if not millennia.
And for centuries, if not millennia. The ocean continues to respond to the atmosphere that we create for something like 1,000 years. And that sea level will continue to rise over that period as well. So we need to prepare for sea level rise. We can debate how quickly and how much, but we have to start asking ourselves some tough questions about what areas we want to protect and what areas we need to retreat from. It's really only a matter of time.
Okay.
Great.
Well, thanks everyone for the panelists for taking part today, and thanks everyone online for tuning in, sending in some great questions. This will be archived immediately after we wrap up here and available on the NASA Explorer YouTube account. That's youtube.com/NASA Explorer. And again, thanks a lot. We might be looking to do a number of other climate topics in the coming months. So have a good afternoon.
Thanks
Great,
for
thank
opening
you.
the door.
Thanks,
for
Patrick.
Thanks.